So in our final example here, we're going out to a busy restaurant. They're serving 200 customers that night, and we're kind of looking at it from the restaurant's point of view. 125 of their customers ordered appetizers, and 110 ordered desserts, and 170 of those customers ordered at least one of an appetizer and or a dessert. And the question is, how many ordered both appetizers and desserts? So quickly, I need to set up some events here. My colon equals, remember, means defined to be. I'm just going to, for short, I'm going to say A is the set of all people who ordered an appetizer. If I could remember how to spell appetizer, it would help. Appetizer. B is the set of all the people that ordered dessert. And we're asked how many ordered both. Both means we're looking for people that ordered an appetizer and a dessert. So that's the intersection. So we're trying to calculate how many people ordered both. Now, our original rule for inclusion and exclusion on two events, if you go back and look at it, the very first slide in this lecture, we had the formula A intersect B. The number of things in A intersect B is the number of things in A plus the number of things in B minus the number of things in the union. And we can calculate all of these directly from the problem stem. A is the number of people who had appetizers, and it tells us that that's 125. Tells us that up here. B is the number of people who ordered desserts. There's 110 of them. But 170 people ordered at least one. That's the union right there. At least one means a union. So we're going to subtract off 170 here. And now let's just do the arithmetic. We get 235 minus 170 is 65 people. So we must have had 65 people ordering both an appetizer and dessert at this particular restaurant. Ordered both. That means they're in the intersection of A and B. They're in both A and B. So that was probably easier than some of our other problems here, but let me make sure that all the steps are really clear. First thing to do is to set up events, A and B. People who ordered appetizer, people who ordered dessert. And then we're asked how many people ordered both, which means we're counting an intersection. So we're going to count an intersection. We're going to use the formula for inclusion and exclusion that we had back in the very first slide. So you count the individual events and then you subtract off the union. And we know the size of those because it's given to us in the stem of the problem. 125 ordered appetizers, 110 ordered desserts, and 170 ordered at least one. So that's the union right there is the 170. And then we just run the arithmetic here, and we end up with 65 people ordering both appetizers and desserts. 65 people in the intersection there. Interesting point about this problem is that this 200 customers total in the restaurant appears to be a red herring. It doesn't appear to be relevant at all to solving the problem. So you don't always have to use every number in the problem to get your answer. Often the way problems in homework exercises are set up, you use every number, but it's not always true. Sometimes there's some red herring information there. So that wraps up our lecture on inclusion exclusion. I hope you'll stick around for some more lectures. We got some good stuff coming up on independence and on Bayes' rule in the next couple of lectures. These are the probability lecture series here on Educator.com, and my name is Will Murray. Thanks for watching. Bye-bye.